Space debris, often referred to as space junk, consists of human-made objects that no longer serve a useful purpose but continue to orbit the Earth. These objects range in size from large, defunct satellites to small fragments of spacecraft, such as flecks of paint or bolts. The problem of space debris has been growing since the launch of the first artificial satellite, Sputnik, by the Soviet Union in 1957. As space exploration and satellite deployments have intensified over the decades, the amount of debris in Earth's orbit has accumulated significantly. Currently, it's estimated that around 40,000 larger pieces of space debris are tracked by organizations like the U.S. Department of Defense, which actively monitors the orbits of these objects. However, these figures only account for the more substantial debris. It's believed that an additional 500,000 to 1 million smaller objects, too tiny to track, are also present in space, adding to the complexity of the problem. The modern world relies heavily on satellites and space infrastructure, making the issue of space debris even more pressing. Many critical services that are part of our daily lives depend on space technology. For instance, weather forecasting, which allows us to predict storms, heat waves, or natural disasters, relies on satellite imagery and data from space. This information is crucial for agriculture, disaster preparedness, and everyday planning. Similarly, global positioning system technology, which is essential for navigation, transportation, and logistics, is powered by a network of satellites in orbit. This GPS technology is not only used in smartphones, but also plays a pivotal role in enabling emergency services, air traffic control, and the military to operate efficiently. In the financial sector, space technology enables secure and accurate transactions. Many global financial institutions rely on satellite-based timing signals for transaction processing. A disruption in this infrastructure due to space debris could potentially cause widespread financial chaos, halting credit card transactions, ATM services, and even stock market operations. Communication satellites, which provide internet services, television broadcasting, and long-distance communications, also occupy critical orbital pathways. Any significant damage to these satellites could disrupt global communications, affecting everything from personal connectivity to international business operations. The modern way of life is deeply intertwined with space infrastructure, and any threat to this network poses significant risks to society. One of the most concerning aspects of space debris is the size of the objects and the potential hazards they present. The size of debris can vary dramatically, from large, defunct satellites and spent rocket stages to small pieces of shrapnel from previous collisions. While the larger objects are more easily trackable and can be monitored for potential collisions, smaller debris poses an even greater challenge because it often goes undetected. The size of space debris plays a critical role in determining the risks it poses to operational satellites and spacecraft. Larger pieces of debris are essentially dangerous because they can initiate a chain reaction of collisions, a process commonly referred to as the Kessler syndrome. This phenomenon was first proposed by NASA scientist Donna Kessler in 1978, suggesting that as the density of debris in low Earth orbit, LEO, increases, collisions between objects would create even more debris, leading to an exponential rise in potential collisions. Over time, this could result in orbital regions becoming so cluttered with debris that they're no longer usable for satellites, space exploration, or other space-based activities. For example, a defunct satellite or a spent rocket stage could collide with another large object, shattering into thousands of smaller pieces. Each of these fragments would then have the potential to collide with other objects, multiplying the amount of space junk and further increasing the chances of future collisions. This self-sustaining process could make certain orbits so hazardous that they become effectively unusable for decades or centuries, which would have severe implications for space-based technologies that the world relies on, including communication, navigation, and weather forecasting systems. Even small pieces of debris, such as fragments less than 10 centimeters in size, are dangerous in space due to the extreme speeds at which they travel, up to 28,000 kilometers per hour. A small object, such as a paint fleck, can cause significant damage to a spacecraft or satellite because of the immense kinetic energy it carries at such high velocities. For instance, NASA has reported cases where space shuttle windows were replaced after being damaged by debris smaller than a millimeter in diameter. The cumulative impact of collisions involving both large and small objects increases the urgency of addressing space debris as an international concern. Recognizing the dangers posed by space debris, numerous efforts are currently underway to mitigate the problem. One of the most effective strategies being developed involves designing satellites with deorbiting capabilities, which means equipping them with the ability to safely re-enter the Earth's atmosphere at the end of their operational lives. This would allow satellites to burn up upon re-entry, preventing them from becoming part of the growing mass of space junk. This concept is particularly important for satellite operators, both commercial and governmental, as it represents a proactive step toward limiting future debris accumulation. Space agencies and private companies are also working on improving collision avoidance systems, which help satellites and spacecraft maneuver out of the path of potential collisions with debris. This requires effective communication and data sharing between national space agencies, private satellite operators, and commercial space companies. For example, space operators can use radar tracking and other technologies to monitor the position of debris in orbit, allowing them to predict potential collision events and take evasive action. Enhancing these systems can significantly reduce the likelihood of catastrophic collisions, but it requires close cooperation between various stakeholders in the space industry. One of the major hurdles in managing space debris is that space is a shared resource. No single country or organization owns the space environment. This makes addressing the issue politically and diplomatically complex. While many nations are aware of the growing problem, effective space debris mitigation requires international cooperation. Nations must agree on rules and standards for operating in space, managing satellite lifespans, and reducing the creation of debris. Some progress has been made in this regard. For example, in 2022, the U.S. Federal Communications Commission, FCC, introduced new regulations that limit the time decommissioned satellites can remain in orbit. Previously, defunct satellites could stay in orbit for up to 25 years before needing to be removed. Under the new rules, this period has been reduced to 5 years, encouraging operators to deorbit satellites more quickly and thus reduce the potential for them to become space junk. International agreements, such as the Outer Space Treaty and the UN Guidelines for the Long-Term Sustainability of Outer Space Activities, have laid the groundwork for responsible behavior in space. However, enforcement remains a challenge, as there are no comprehensive mechanisms for ensuring compliance, especially with the growing number of private actors in space. Diplomatic efforts need to continue to focus on establishing clear rules for all spacefaring nations and organizations, alongside mechanisms for holding parties accountable when debris is created. If the issue of space debris is not addressed in a timely and coordinated manner, the consequences could be dire for both current and future space activities. One of the most immediate impacts would be a shortened lifespan of operational satellites. As collisions with debris become more frequent, satellites could be damaged or destroyed, necessitating costly replacements. This would not only increase the expense of maintaining satellite constellations, but could also lead to gaps in critical services like GPS, communication, and environmental monitoring. In a worst-case scenario, certain orbits could become economically unviable due to the sheer amount of debris. Companies and governments would face enormous challenges launching new satellites or conducting space missions, as the risk of collision would be too high. This could stifle innovation and progress in space exploration, curtailing missions to study other planets, develop space-based solar power, or even send humans to Mars. Inaction could also increase the costs of space insurance, further complicating commercial space activities. In addition to preventing new debris, several technological solutions are being developed to actively remove existing space junk. One of the most promising projects is Clear Space One, a Swiss-led mission that aims to remove a defunct piece of debris from orbit using a robotic claw. Scheduled for launch in 2025, Clear Space One will target a piece of debris called Vespa, a payload adapter left in space after a previous mission. The robotic claw will latch onto the debris, capture it, and bring it back into Earth's atmosphere, where it'll burn up during re-entry. This mission presents significant technical challenges. The debris in orbit is not stationary. It's traveling at high velocities and may be rotating or tumbling. The Clear Space One robot will use machine learning algorithms to synchronize its movements with the debris, ensuring a precise capture. Success in this mission could pave the way for larger-scale debris removal efforts, demonstrating the feasibility of such technology and opening the door for commercial debris removal services in the future. Experts agree that prevention is the most effective solution for managing space debris. Future satellite missions must be planned with debris minimization in mind, including the use of deorbiting mechanisms and careful management of satellite lifespans. This means designing satellites that can either re-enter Earth's atmosphere after their mission or be moved to graveyard orbits, far from the operational zones of active satellites. At the same time, international regulations need to be strengthened and expanded. Governments and space agencies must work together to create enforceable rules that apply to all actors in space, including emerging private companies. Clear guidelines for satellite disposal, debris management, and active debris removal are critical for ensuring the space remains accessible and safe for future generations. In addition to preventative measures, cleanup technologies like Clear Space One will play a crucial role in addressing the existing debris problem. By combining innovative technologies with effective policy frameworks, the international community can mitigate the threat of space debris and ensure the long-term sustainability of space activities. Share your thoughts about this in the comments below. And if you want to know more about the threats in space, watch our video on quantum entanglement, spooky action at a distance. See you in the next one. Bye.